great pleasure to Katharine Turner, who will be speaking to us on PCA of rank functions with case studies, processes, colloids, and sphere packing.
Thanks, Peter, and thanks to anyone here. This is really welcome to my computer. Okay, so today will be rather data heavy and a little exploratory rather than proving a lot of theorems. And the motivation behind this is we're given data that is distributions of a local behavior. Right in front of me, I have some examples from colloids. So the idea is there's slightly magnetically charged liquid, and there's little iron balls in there. And depending upon the temperature, you can have different phases in terms of the distribution of these iron balls. So each of these points here is the center of a different ball. I mean, they're quite small balls. So what you can see is that the one on the left has a bit more structure than the one on the right, but a whole lot of subtle, small differences. What sort of distributions of sort of points in the persistence diagram are, but using a different sort of way of capture this topological summary. So, homology, I'm going to assume for the large part that everyone here has heard of this, and this is just sort of a reminder. So the idea is we're summarizing how the homology evolves over some filtered topological space. All homology groups will be calculated over Z2, or so, but really Z2. So we start off with the filtration. Filtration will be data determined. So we will be looking at distance to the set of points here. Okay, we have one value less than another. We have an inclusion from K into KB, and that will induce a map on homology. Okay, what we're going to look at is this rank function. So the idea is that for every point, every point above the diagonal in the plane, you can think about what the rank would be of this induced map on homology. Okay, it's very related to persistence diagrams. You can think of it as the number of points in a corresponding region of the plane. Yeah, they're equivalent information. So just to the dimension of some space of homology classes that are born sometime and are still alive by some other time. Okay, so traditional Betty numbers, which is why we use the beta notation. So this is not sort of looking at a distributional kind of one or a distance function type of filtration. This is just a made-up example to try and illustrate what these things look like. So at the top, we have this filtration K sub T, and we're capturing the information and just describing it as a function above the diagonal on the plane. So by colors, the colors here correspond to different numbers. So, you know, V0 gives you the connected component, so it will contribute something which is sort of that big yellow region. Similar idea for H1. So here there's only one interesting H1 persistent H1 class. So you've got a function which is almost everywhere, but over a triangle it equals 1. Okay. Things we'll care about will be sublevel sets to distance functions. So this is just a picture of an example of, well, we've got a set of points in some place, and we're just looking at how we would expand balls around those points and looking at the union of those balls. KT will be the union of balls of radius T. We do this via the check function. So we have our set of points. We turn over the complete simplex, where we add in a simplex when the intersection of the corresponding balls is not So here's a little picture. These were perhaps my balls. I've got some radius, and then I have simplicities added in. Other things intersect appropriately. So the analysis of this gives us the same homotopy class for every R, and that we get the same persistent homology from the filtration from sublevel sets. This is basically justifying that when we compute things, we get the right thing. Okay, so let's just try and think a little bit. Yeah, this is just a very much boring overview until now. Compute me. Assurance. Good. Okay.
I can hear you.
Good. All right. So the space homology rank function. So instead of looking at the space of diagrams or the space of barcodes or the space of Euler characteristic curves or whatever, we're now going to use this slightly different way of writing this persistent homology information in a sort of functional space. And now we're in this nice, happy functional space, we'll be able to do statistics more easily. Okay, so this is very similar to the idea of landscapes, except it's actually, it's philosophically, but it would be very different in practice in terms of the results you get out. Okay. So the space of possible rank functions will be functions that go from above the plane to the positive integers and have some sort of monotonicity condition. But we won't really restrict ourselves to that space. We're going to put it inside that larger space that goes to real valued functions above the diagonal. Okay, this is a nice happy space. Averages are trivially defined and calculated because you can just take the average pointwise. Okay. For any measure that we have over above the diagonal, we can construct a distance between different persistent ranks. Okay, so we can just take an integral. L2 kind of distances because L2 is nice. You may notice the d mu there. That's just to say, right, this doesn't have to be just Lebesgue measure. You can be whatever you like. Think of what's this L2 space of functions. Well, it will be things whose integral is finite. This is a Hilbert space. It's got a nice inner product, which means that everything works. Any space, we can think of an affine space lying inside the space of functions, which are things that are a finite distance to it. I guess another way of thinking of it is we can take our L2 space and we can just shift it to sort of around H. Okay, so it's the sort of idea that we're going to use to say, right, suppose we have a set of functions that are lying in some affine space. Well, then we can just recenter them to then get a set of functions that's in L2. Okay. Similarly, what we're going to do is we're going to take the mean options and then we're going to center using the mean. Okay, in zero sort of result. So to reiterate, the idea is that you have a bunch of things. You just process them to get your persistent homology rank functions, and then you can take away the mean of those persistent homology rank functions to get a new set of functions which will have mean 0. And that will be hopefully in this L2 space. Okay, so all right. Now, I guess as in much of statistics, there's a certain amount of choice involved. And you have to make choices and then move on. You certainly don't want to pick everything because then you have a multiple hypothesis testing problem. But things that we have to worry about is this choice of what mu could be. So obvious choice would be, okay, let's just take a Lebesgue measure, but there's no reason why you have to do that. Things we really wanted to satisfy is that if we took two different simplicial complexes, okay, and we considered corresponding rank functions that whenever the beginning and end state of the stations are the same, and it only changes finitely many values, then the distance between the corresponding rank functions should be finite. Okay, this is my basic requirement that I want this to satisfy. It seems to me a very reasonable sort of requirement. I mean, yeah. So, measure we're going to have problems just with this example because essential classes might attack at different times. Okay, so this example that we have here is that, well, all right, let's say we have K and L, and it's just of the, and it will appear at time 0, or it could appear at time 1. Now, if you, then you're going to have this sort of column where they differ, where the inhomology rank function will differ, because the will be 1 everywhere for x bigger than 0 for k, but it will be only 1 for x greater than 1. So you have difference over here, and if you took Lebesgue, if you measure, they're getting integral of 1 over an infinite strip, which would be infinity. So one other thing we could do is we can say, all right, instead of just taking Lebesgue measure, let's sort of do a weighted version of Lebesgue measure where we just weigh by how far away from the diagonal you are in some way. So we're going to have this function phi, which will, you know, which will decrease as you go away from the diagonal, and we'll take the integral of phi times Lebesgue measure. Okay. Now then this will not become a problem as soon, this previous example won't be a problem as whenever phi is integrable from 0 to infinity, because then you'll end up having these, basically you'll have something along this strip, along that strip it's finite, not a problem. Okay, and I guess the key point to say is that this is exactly the condition that will mean this will always work. We're going to phi that is along those lines. Okay, so we'll take our phi, the x of minus the distance. So this means that we're in that scenario where everything will just work. I mean, as I need to necessarily use choice, you could pick Lebesgue if you knew that all your essential classes started at the same time or something like that. So this is just a sort of rating in this context that, look, if we do have persistent homology rank functions that come from check filtrations of different finite point clouds in RD, this means that we have the same k minus infinity and k infinity, then all of the rank functions will lie in an affine space. In affine space because each of the pairwise distances is finite. Because they lie in a finite, they also lie in a finite space containing the of them. Okay, in fact, sort of average of the center is 0 again. Okay, lie in most in n-1 dimensional vector space, living inside this, you know, infinite dimensional Hilbert space of functions. So, I don't know how many people are familiar with PCA. So P stands for principal component analysis. It's, you know, sort of one of the first pass things people use in statistics, particularly if they want to have a picture. But really, it's linear algebra. So we have a product on some vector space. Okay, PCA is finds a set of principal component weight functions that just, you know, which will basically describe a basis for the best subspace that you could project things onto. Define these principal weight components inductively. The first one will maximize variance that you would if you projected onto that line. Do the next one by saying, well, given have to be orthogonal to that first choice, what thing that will capture the most variance of projecting onto that, and so on and so forth. And the idea is that when you've done them, you've found the j-dimensional plane which projected on will be the best way of capturing the information of data that you have. Okay? Call the coordinates in these different spaces the scores. Okay? So this is a term often used to sort of describe how reasonable using PCA in some setting would be, and in particular what dimension they do it up to. So if you take the variance of the scores, it will be the sum of variances in each of the dimensions. So the proportion of the variance in the first case, or in the case, sorry, will be the sum of the variances in the first divided by the sum of all the variances. Okay? So the standard way to compute PCA when you've got some sort of nice multivariate data is each row a different piece of data, each column is a different variable or a different coordinate, and then you compute those x and an eigenspace eigenvalue decomposition. So the eigenvalues are the variances, and then the eigenvectors are going to be the directions. And so you should order them so that the first eigenvalue is the first one you look at. Slight problem in that, well, one, we're looking at an infinite dimensional space, and so even if you discretize, it's going to be huge. The other thing we're going to have a problem with is that we've weighted the different locations. So I want to just think of normal inner product as being the normal inner product of two vectors. Representation doesn't work quite so well. To do this is to think about these maps x and x tilde, which we previously thought of as just as matrices, in terms of what the linear maps are. So x can be thought of as a map that takes any function to a set of inner vector where each coordinate is the inner product with one as. And transpose can be thought of as taking linear combinations. So from very large space to nice happy finite dimensional space, X transpose goes from nice finite dimensional space to large infinite dimensional function space. Because look at X transpose, okay, that means that we're going to go have a nice happy matrix representation where we've got the matrix where the ij entry is just the inner product of fi with fj. So it means that what we're really going to just do is calculate squared inner products in order to create, well, this okay? We X transpose, we want X transpose X. So do we just how to relate the eigenvalues and eigenvectors. So it's a relationship between these things where eigenvalues of one, non-zero eigenvalues of one and non-zero eigenvalues of the other, and can figure out the corresponding eigenvectors just by multiplying by X transpose. So that we can find the eigenvectors and eigenvalues of X transpose and then find the appropriate principal component weight functions by taking the appropriate linear combinations of our sample Fi. Okay? I guess one thing to point out here at this point is that these the weight functions are sort of unique up to sign. You could equally valid as a choice. So and I guess I should have said this earlier, the rest of the talk is very data heavy. Okay, so this is just a look at what happens if we try and do this sort of analysis with real and simulated data. So another 4 colloid pictures to in fact repeat. The top two, so just going top, bottom left, bottom right, 4 different increasing temperatures. So the temperatures were labeled 13, 14, 15, and 16. Now 13 and 14, so 13 and 14 are in the crystalline phase, 15 is in the exotic phase, and 16 is in the fluid phase. And you can kind of see that they're quite regular in the top 2, and becomes more and more kind of disordered and random and sort of fluid, I guess, as you get to higher temperatures. So we have 7 of these samples. So the samples, you know, picked windows so that they've got the same number of points in them. Okay, so 7 of 13, 7 of 14, 7 of 15, and 7 of 16. Okay, and I guess the question is, can we figure out which phase something in, temperature it's in, just using these principal, using the persistent homology rank functions, and in particular using the scores in the PCA. Okay, so just have got some pictures here. So just looking at H1, so the dim equals 1 is just saying, oh, well, I'm looking at H1. I have the first picture here on the top left is the mean. Okay, so you're getting a lot, actually, this sort of shape of just increasing things as you go down. The second one here on the top, so the top right, that's the first principal component weight. So I guess one of the other advantages of functional principal component analysis is that you information about these directions, these principal component weight functions, may be able to tell you something. You might be able to figure out the structure of your data by looking at these directions as well. So that's principal weight component. And then the bottom one here is the second principal component. So the proportion of variances I've got written here, 86% is a lot in of itself. You know, the very reasonable amount to just leave it at that. So just a graph. Just look at the scores. So x-axis is the first principal component, and along the y-axis is the second. It might be worth noting that the scales are very different. So this is really like a squished version of you should probably squish the y direction a bit in your head. That top not actually that far from the other. So color-coded these depending upon which of the 4 temperatures it is. These black ones and these blue ones are the same. Black ones are crystalline, as is blue, so 13 and 14. Then 15 is the hexatic, and then 16 is the fluid. And you can see that these split up quite nicely. And the fact that the black and blue are kind of closer than the others to each other, then what I'll consider them the same phase. Something that's worth pointing out is that the calculations in terms of this H1 is looking at how close are 3 neighboring points to being corners of an equilateral triangle. Okay, so H0, here's some pictures. So the average one, and the first principal component is the second. Proportion of explained variance is ridiculously high. And the H0 persistent function is exactly lying on this one-dimensional subspace of this function space of all possible for R2. This here is just a plot that's sort of showing how the first principal component for H0 is related to the first principal component of H. And I've got these colored by the different temperatures. And you've got this very clear clustering. Well, one is where you get this very clear clustering into these different things. Oops. Okay, the data I have for the moment on the colloid stuff. I'm on to an example which is about sphere packing. Okay, so the scenario in this situation is you have a container and you fill it up with the same guy, and you have a couple of choices here. You kind of just pour them in and they'll pack themselves however you like. Or you could pour them and agitate them a little so they try and settle down a bit more. You can get a really fancy machine and your container of balls in this really fancy machine that will shake it really vigorously so that it will find lower local minimums in terms of, well, local maximums in terms of dense packing. Okay, so you can get partially crystallized sphere packings using this very, very vigorously shaking machine. Okay, so what we have here is we're looking at the persistent homology rank functions in H2 for the crystalline versus the disordered.
Sorry,
yes?
Can I interrupt you? So homology, I guess maybe in this example and the previous one, you have points in the plane.
So the points in the plane. Oh, I guess I should have explained that better. This colloid data here is that they have liquid on a plane, and it's so thin a plane that it really is two-dimensional.
And the persistent homology of the
check
complex.
Yeah, everything is check.
In this latest example, we now have
point in R3
box.
Yeah, we're in a box, and then we don't look at the whole box. We take a smaller bit from the center to hopefully make the barrier effects less an issue.
I see.
It's a bigger box, and then take a smaller viewing thing within, and in some way to try and make sure you get the same number of points. I can't remember exactly now the details. So that you've now got the points, centers of each of these. Okay, so
all the same radius.
They're all same radius.
Okay, and you're constructing a check complex from those in your box.
Yes.
Okay, thanks.
Thank you. I find this very hard to talk to you. Okay. Look at the mean rank function of the most crystalline. It's got an interesting structure. I'll talk about a little bit. So you can see that there's this sort of very red section here, which means a very high value. So there's a very high value here, and these points that sort of happen at a corner near the bottom correspond to the point being on a tetrahedron. So 4 points on a tetrahedron. If I had 4 points exactly corners of a tetrahedron, you would have some point around here, and then you have slightly warped tetrahedron because it's not quite perfect a packing, but they're kind of in the same sort of vicinity. So you've got a slight smudging effect, but generally speaking, there's a lot of points just there are approximately a shape of tetrahedron. And the point of where you've got this sort of bigger blue thing up to about 0.07 is looking at if you had the points on the corners of an octahedron. Had one point on the corner of a octahedron, you would have a point around here, and if you have a slightly sort of warped version, it would be slightly off that exact point, but it's only that variation. So you've got these two big, almost like multiples of indicator functions over these big triangles. Okay, I hope that. If we, and I get to point out here that if you have the perfect sort of sphere packing in R3, you're going to be a combination of tetrahedrons and octahedrons because you can't tessellate with tetrahedrons, so you need to put some octahedrons in there as well. In comparison, you've just got sort of, a smudged out effect with the mean rank from the disordered. So the idea is that we have a whole lot of these disordered sort of packings, and then complexes of the centers of these, you get these different rank functions, and it doesn't have any of that structure that kind of shoots out at you saying, oh, look, you must have a lot of this local distribution. So the first principal component of these H2 persistent homology rank functions is really just how many octahedrons do you have? Okay, so this is basically all it's saying. It's saying, is it closer to the crystalline or is it closer to the disordered? It's worth noting that when we do these pictures, unfortunately, we haven't yet done it so that the color scaling is the same for each picture. So the colors got to 9,000 on the first, and they got to 2,000 on the second. So it's a smaller effect happening in the second picture. Why what matters is multiple are you of the first. Okay. So we've got about the fraction versus this first principal component score. Okay, I've got colored points, so I should describe what they're coming in. So blue be pouring, let's not do anything about them, kind of ones. Okay, so that was just sort of very disordered. The gray, they were put in and then slightly agitated. I think they were stirred in some way. Okay, and then these red ones are the, shake. And I think the thing that's important to note here is that the disordered packings are quite stable in terms of their persistent homology rank function. The homology rank function doesn't vary nearly as much amongst each other, okay? So crystalline ones vary a lot. So in your PCA, it's the variation of the crystalline that really drives what that first principal component is. I don't have it here. The portion of explained variance from the first principal component was about 92%, I think. It was certainly 90. So also at dimension 1 instead of dimension 2. So dimension 1, I mean H1. So this is looking at the H1 persistent homology rank functions. So this is all of them, not just crystalline and disordered. So you can see that the feature that comes out of you is this the sort of triangle in the mean, which is the thing on the left. The thing on the left is the mean, and it's got that corresponds to when 3 neighbors are on an equilateral triangle. And if in principle, the first principal function, it really does care just basically how them really are looking like an equilateral triangle. Now think about when you did a real close pack, do I guess it's not just equilateral triangle, but other ones. But you get a packing, a real efficient packing, and you're going to have a lot of equilateral triangles everywhere. I mean, when you're in your octahedrons, their bases are made up of equilateral triangles. Well, I hope. I just got a weird little buzz in my ears.
Might have been me, Kate.
Okay.
Can you fix that picture a little bit more? So the figure on the right is really striking. So the blue.
So the blue is here.
So that assuming is coming exactly from the measurements on an equilateral triangle. That if you have an equal triangle, that a cell that's born according to the distance between the.
Yes, so you can sort of, it's born at sort of 1 and then dies at root 2. Is that right? Root 2, whatever the number is.
Okay, excellent, yeah. And then, all right, great, so I understand that now. And can you explain the red?
Red is negative. So, I mean, the thing is that, you know, because things aren't exact packings, there's sort of disorder amongst them. Okay. You got sort of, you know, a matter of some things aren't exactly that shape, they're going to be a slightly different shape, et cetera, et cetera. And when you look at the mean, you've kind of got this sort of slant coming off. And I think that might be something to do with sort of variations of this shape, not quite being equilateral, but sort of being off it. So about this, if you have a triangle on the side of an octahedron, what happens? Yeah, but it's certainly related to both of the things. I mean, all the H1 persistent homology is very much related to sort of 3, you know, triples of points that are by each other and how it's positioned in relation to each other. Under your question there, but
That's helpful.
So again, the first principle, first scores for H1 are highly related to the volume. So the same coloring as before, the blue is disordered, green is pre-ordered, and red is crystalline. Okay, so sort of all I've got for sphere packaging. And so the examples are of a simulated kind. So one standard problem in looking at patterns, know whether something is completely spatially random. So a pattern here is a set of points in some space. So I'm just going to leave myself in the square. So I've got a square, and I can plot points in it. Okay. If I want it to be completely spatially random, then that means that each of my points will be drawn independently. Okay, and they're each going to be drawn from some uniform distribution over the square. So every point is just as likely, and every point is drawn, you know, in the square is just as likely, and every point is drawn independently of each other. Okay, so this is very much like a Poisson distribution, but here I fixed the number of points that you're going to see. Okay, so the question is, given a pattern points, can you say, oh look, you know, with probability this is not spatially random? Okay, so there's sort of a null hypothesis testing kind of thing happening. So should one want everyone here that this is work that's still in the exploratory stage, but it seems to be clear that it seems to be able to distinguish different random versus not random. So the plan is to, instead of analytically say, all right, let me use the persistent rank function and the distribution of persistent homology rank functions, completely spatially random point processes. So the runs are from the check complexes of the pattern. And that distribution is, we can say, all right, you can say if you're outside this range, then you're probably not completely spatially random. Use this to test. So I've just the number of points at 100 and I've units square. I'm going to do it in a Monte Carlo kind of fashion for the moment, at least in this exploratory stage. I'm going to sort of run 400 simulations of picking 100 points randomly. So each of these 400 simulations produce persistent homology rank function. Now I've effectively sampled this distribution of rank functions 400 times. And the persistent homology rank functions for H0, and I look at the ones of H1 separately. Okay. So the that I'm currently pursuing is, randomly being made, is compute the mean and the first 80 principal component weight functions, which is a lot, but I don't actually need to know what these look like. I'm going to be using this as a way to project things down onto a reasonable size space. Okay, and the distributions of distances to this projected space. So how far is a point from this 80-dimensional subspace in space of all functions. I'm also going to calculate. I've said here the sum, what the sum is. So you're looking at the score squared divided by the variance of that score. Is effectively like a z score squared. Okay. So if you had univariate, it would just be the distance to the mean. But if you have, let's just step back. If I have a multivariate distribution in somewhere, I might want to, I effectively have some sort of ellipsoid type distribution. Now I want to capture much of the information. I then scale each of the dimensions to make it spherical and then say, all right, I want to live within some sort of sphere. Okay, so that's my distribution rho 2 within these projected points within the top 8 dimensions. And hope is, all right, find a cutoff for P1 for the rho 1 and find a cutoff for rho 2, and then determine whether some new point pattern is going to be spatially random or not by comparing its value in those distributions of rho 1 and rho 2. Okay, these distributions just so is 400 completely spatially random point patterns. Take the homology functions, subtract the mean, etc., etc. So the first one is sort of their sort of modified distance to the mean within 80 dimensions. I take my cutoff at 0.36 or something like that. I've covered everything. I've only covered everything within this particular set of 400. So, this is unfortunately whatever happens when you're going in a Monte Carlo route. And you can also look at the distance to this 80-dimensional space, and you might make some cutoff, around 12 or even up here or down here, whatever you like. But here's that if you then add a new set of completely spatially random, then high proportion of the time you in those cutoffs. Okay. Do the same thing for H1 instead of H0. Again, the first distribute this modified distance to the mean within the first 80 principal components. And the second one is the distance to that 80-dimensional subspace. Okay. So, I guess I should point out that these things binomial and you have 5% of them in terms of satisfying those cutoffs. What you do, you want to have sort of a 5% kind of cutoff. So one type of, so I guess the goal to then say, all right, let's suppose we draw a whole lot of point patterns from other models of distribution so that aren't completely spatially random, and see whether or not we would not, detect them as not being random. Okay, completely spatially random. So this point pattern, I have an example of one on the left. It's an important example in point pattern analysis, in that it has exactly the same distribution of pairwise distances. So up counterexample, the distribution of pairwise distances will be the same as binomial. So you would never be able to tell just by looking at the distribution of pairwise distances whether or not it was completely spatially random. I think you can tell the difference if you look at three-wise, triples, but not for just pairwise. And I guess on this thing, on the right here, I've just got the distribution of the distances to the have distributions to the first 80 dimensions. Just that none of them are within, 40 of the top 8 dimensions, yet everything was within 40, especially random. So none of them were accepted with the H1 test. Unfortunately, the none is accurate. I didn't manage to just for the other graphs in time, but we ran it with a couple of other types of models, so a clustering model as well as a repulsive model. And interestingly, H1 worked in sort of detecting differences for the repulsive one, and the H0 detected differences for the clustering model. But yeah. Because I'm a
very much. So let's thank Katharine. And people have questions. Maybe I'll start. So you use this nice rank function, and you defined an L distance between the rank functions using this one scale Lig measure. And one question is this stable? So does it give you is this distance stable?
I guess the question is, what are you wanting to be stable with respect to? So the kinds of problems that I could foresee using this system function for are where you're looking at distributions of things. So you're not caring about the exact locations of things. Are there 100 that satisfy being in this box, or are there 200, or are there 102? So sort of normal stability with relation to, say, how does it relate to bottleneck or whatever, it doesn't seem to be quite the right question. Because sort of distribution scenarios, you don't actually care about what the bottleneck distance will be. You're caring about whether or not you do half of the triples correspond to equilateral triangles, or do a third of them, or do all of them. So be stable with respect to any of the normal stuff we do, sort of stability with respect to. So if you just shifted one point a little bit, it's going to be different over sort of a patch, okay? But taking the square of the differences, so that could make a big difference in total.
I'm surprised because my feeling was that it should be stable.
Are you saying that if F and G are L close or something, then their homology rank functions should be close? Is that what you're saying? Something along those lines?
Maybe something along those lines, yeah.
I mean,
I guess maybe you might need something stronger than...
You would need something stronger, because if you had something like you had a little triangle and it had value n on it, that's when you're getting an n squared type difference integral, even if it's over a small patch. So you might be able to relate it to some sort of Wasserstein distance between the diagrams. If you had, you could get a suitable bound where you've got a constant involving, say, that the functions are the amount in some region, outside some region, or something like that. Yeah, it might be. I guess, is whether or not that's what tell me about the sort of problems that I might apply this to.
You probably want some sort of stability in the sense that you want the end results to not depend on really small noise in your measurements. I think it seems that you're able to say something in that direction.
If you have very small amounts of noise, then that means that you're only going to really be making differences over noise is significantly less than sort of the features of which things is happening. Probably the functions will be identical over a large amount of the plane. So the integral should be close. Does that make sense?
Yeah.
How you would formulate such a theorem, in terms of bounding these different things, I wouldn't know how to go about.
Okay, thanks. Questions?
Yeah, I have a sort of question. Yes. Can you hear me? Oh, okay. Most important person. Yes. I was wondering, what's the sort of major requirements on these rank functions that enable this? Like, have you thought about functions that are some more general functions on barcodes, like the order functions on barcodes that do this stuff? And do you have any if you thought about that, do you have any idea what that might tell you?
So you probably could do stuff involving those. Those are things like the squared distances to the, you get a bunch of different functions, if I remember right, the sums of the distances to the diagonal, or the sums of things like that. Yeah, I think you probably could do a similar kind of thing using it within that function, that different function space. I guess that as soon as you put things in an appropriately nice function space, then you can do functional PCA, and it should work. So there's only sort of two iterations. Is one, how difficult is the computation within that space? And the second thing is, how appropriate is that particular setup to the you have to analyze. But I've got some functions that gonna, was talking about. Some be easier than others to compute when you have thousands and thousands of point.
True.
So it would be quite easy if they're just distance to the diagonal, then you've got some sort of cumulative distance thing, it would be fine. Some of them are more, different ones, you might end up sort of exponentially snowballing into some horrible twirly couple beach ball of Mac goodness. The thing is, I guess, whether it captures the kind of information you want to capture. And the reason why we looked at these functions in this particular scenario is that we have these very geometric problems where you have little local distributions of things happening, and if you have a particular local distribution, it will mean that you're getting a point here. If it's slightly off, it will move slightly, but you can kind of see in these pictures when you have a big sort of jump in this homology rank function, it means that a lot of some very specific local sort of scenario is happening. So I guess the question would be, if you were taking this other setup, where you have a kind of function of these points, whether it is capturing that same kind of behavior, or whether they might work much better for some other problem which wasn't this local geometry type problem.
I see. Thanks.
All right, let's. I'll thank Kate again for a very nice talk. Thank you. Thanks a lot, Kate.